So what are we discussing? We are discussing about a VCF file and the parts of a VCF file. And what is it that is not there in the VCF file that has to be there in the PED file for it to be called into for the GWAS analysis. So now, if you look at this, for your ease of understanding, what I've done is I've taken an example. How does a PED file look like? For example, now, if you look at this, right? See, your VCF basically contains what? Your VCF contains the chromosome ID, the position, all the variants, and all that. So this VCF initially can be converted into a file called as a PED and a map file. PED and a map file. I know that most of you know it, but let us revise this once again so that there'll be more clarity on what a PED file is. Now, for example, so the columns have to exactly match. They cannot be anything less than what it is there in the VCF file. So they have to be there in the PED file. Yes, anything excess of whatever is there can also be there in the PED file. So look at this. So you have these sample IDs, all of you, onto the board here. Like you have these sample IDs, right? Sample 1, sample 2, sample 3, sample 4. All the genotypes are called here in the PED file. If you look at the PED file, all the genotypes are called here as the sample 1, sample 2, sample 3, and sample 4. You got it? Now, what you have here is, right? Just a correction only to make you understand this. Purposefully, I committed. Listen to me very carefully. See, the major difference between a PED file and a VCF file is you do not have your samples here in the columns, but you have your SNPs. This 1, 2, 3, 4, 5, 6, 7 are nothing but your SNPs. Is that clear? Remember, that is the major difference. That's why I wanted to just see. You have samples as columns in the VCF file, whereas here in the PED file, you will be having SNPs as columns. SNPs as columns, right? Now, where do the families go? See, where do the families and the samples go? The samples will be now row-wise. The samples will be now row-wise. For example, now there is a sample 1 here, let us say, and this sample 1 has got an ID, let us say, for example, you have a sample 1 here. See, you have a sample 1 here. It has got a family. Let us say in terms of, I'll first put it in terms of human populations, like Indians, right? Under Indians, you give an ID saying it as he's an Indian 1, right? Similarly, the second family ID will be an Indian again, and it will be an Indian 2, some other sample from some other biological replicate. So, but this family ID for all the Indians will remain the same, but this will be a separate sample here. So what do you have? It is a sample here, sample 1 here, sample 2 here. So this family ID will remain the same for the samples belonging to the same family. We talk about a different family. Let us say Americans. You just put it as Americans here. Then the ID of the sample will be American 1, American 2, American 3, and American 4. So you can have as many families as you want, and you should have at least for your variant analysis 50 animals per or 50 samples per family. 50 animals per family. Right? That is a minimum requirement, right? For your normal variant analysis. But if you want to go to for GWAS, listen to me very carefully. This number has to be 100 per family. Means there should be at least 100 individuals considered under the family Indians. There should be at least 100 individuals considered under the family Americans to move ahead and go for the analysis. Now, The 6 columns that are there in the PED file are the most important thing. What do you have in the PED file? The 6 columns. See, the 6 columns that are there are, right? The first one, the samples, the major difference. We committed a mistake. So now you'll remember this fellow initially committed a mistake and then corrected himself. I do it this way so that you remember, yes, the mistake was committed purposefully to make you understand. The samples are in the form of columns there. Now the samples are here in the form of rows, right? So now each sample will be having a family ID here. Will also be having an individual ID here. And for that sample, you'll be having a sire and dam. When you say sire, it is the father. When you say dam, it is the mother. And you also have the sex of that particular sample. And what was I talking about? If at all you want to go in for GWAS analysis, the first thing that you'll have to do is what? You should have your phenotype. Now, let us say, what is the most common phenotype that people ask for as far as human beings are concerned? How tall are you? Right? Let us say, how tall are you? So when you talk about height, so you can measure it either in centimeters, feet, or inches. So this measure will be coming here for every sample. You understand? Right? And these information which are there in the PED file, the 6 columns, 1, 2, 3, 4, 5, and 6 columns will not be there in the VCF file. See, the first difference is what? VCF file will be having samples as columns, whereas PED file will be having rows as columns. In addition to that, you'll be having here SNPs as columns. And for every sample, you'll be having a detail of 6 columns. That is the family ID, the individual ID, the sire and dam, the sex, as well as the phenotype. Is that clear? So this is how a PED file looks like. So if you are looking into a PED file, so this is what is a PED file looking like. Now, where did the information regarding the chromosome, the position, the reference, and the alternate allele go? So what did I tell you? A VCF file is basically converted into a PED file and also a map file. Is that clear? So the whatever you are looking here is nothing but a PED file, and the rest of the information that has not been given in the PED file, like the chromosome, the position, right? Next, the reference and the alternate allele. And you also have, what else do you have in your map file? You also have your genetic distance. That is not generally not available for our studies. That's possible only for plants, right? So you have all these columns, and this is a separate file along with the PED file. When you convert your VCF file, you'll be getting a PED and a map. PED consists of these columns and the map consists of this. These two together would constitute one single file that can go into your analysis for GWAS. Today we are going to do GWAS completely, but we are going to study the fundamentals of GWAS till 3:30, guys. Let me tell you. The fundamentals will go on till 3:30, and then I'll start a practical and we'll finish up the practical. My student will come and she'll demonstrate the practical there itself. Okay. Now, see, now what happens? All said and done. This is very clear that we have now converted our VCF file into a PED file. So what do you have? You have a VCF file. This VCF file is converted into a PED and map file. That's what we have studied. Now what happens? This size of the PED and map files is quite huge. So this PED and map files are further converted into binary format, and they are called as BED, BIM, and FAM files. BED, BIM, and FAM. Now, what are these BED, BIM, and FAM? We'll just go back to the previous one. You see here, the PED file having the information of the family. if you have the information of your entire family here, this is going into this particular part. This entire thing is a PED file, right? And this PED file, to reduce the size, to convert it into a binary format, this PED file is initially converted into a FAM and then a BED file. BED file includes all the information regarding the SNPs, whereas FAM file includes all the information regarding the family, right? You remember, along with the PED, there was a map file. And this map file is converted into a map file, but a binary form of a map file, and that is called as bin file. So what do you have ultimately when you convert this? So when you convert this PED file, you initially have a family file, one, and you have a BED file, and you have a bin file. And these files are quite smaller because they are in the binary format, and these can be handled by normal computers. Is that okay? Right. So we'll straight away, having understood that now our phenotype, the most important thing why I wanted all of you to understand is, you should understand that our phenotype that we are talking about here is present or can be incorporated directly into your PED file, right? That does not mean that your VCF cannot be directly used for your GWAS. You can use it, but this VCF has to be called in along with your phenotype file in your GWAS studies. Now we'll see what GWAS is, the fundamentals of GWAS, and then slowly we'll get into the detail. Okay. Right, guys. So when you're talking about GWAS, what are we actually talking about? We are talking about a particular phenotype being influenced by a genotype, right? So if you are looking at, we are talking about a phenotype. Normally what happens? You have a phenotype, right? And this phenotype is determined by what? You already know, it is primarily the genotype and the environment and the environment. And there is something else that I'm going to talk about later on. We'll just keep a fill in the blank here so that you have the curiosity that this fellow is saying that there's something else that determines the phenotype. Okay. What is our primary aim, guys? The primary aim is, right, this, there, to find out whether there are any portions of your genome that would govern your phenotype. That is your basic fundamental. We'll take one small example, right? We'll take height as an example because that's easy for us to understand, right? And we'll take one particular genotype or one particular this thing. Let us say at a position in the genome, there is a to T SNP. This is a SNP, right? When I say a SNP, if I ask you immediately what are the possible genotypes of this SNP, you should be able to make out the possible genotypes are AA, AT, and TT. And TT. Is that okay? So these are the possible genotypes. Okay? Now, if you say A to be your reference allele and T to be your alternate allele, right? So in terms of alternate allele, these genotypes can also be coded as how many, in terms of reference allele, in terms of alternate allele, these genotypes can be coded as 0, 1, and 2. What does it mean? How many alternate alleles are present in this genotype? The number is 0. How many alternate alleles are present in this particular genotype? It is 1. How many alternate alleles are present in this? It is 2. This denomination is very, very important in case of your genomic selection and GWAS. GWAS and genomic selection in terms of the alternate allele. All right. So here, hope all of you are listening to me. The moment you feel that it is getting monotonous, let me know. Because I'm not in a class, I don't know how attentive you are. Okay, now we'll say we are plotting this graph here. Let us say we are plotting this for AA genotypes. I'm just taking a hypothetical example, okay? Don't ask me like this happens currently in the world or not. I do not know. So when you're plotting this, I'm just giving you an introduction of how at all you can associate a particular SNP to your phenotype. Now, height is measured on your y-axis. Height is measured on your y-axis. If that is the case, now what happens? Let us say, I'm taking a hypothetical example. Let us say, for individuals of genotype AA, right, the height, the individual for one individual, the height is this much. For the other individual, the height is this much. For the other individual, the height is this much. For the other individual, the height is this much. And for the other individual, the height is this much, right? And similarly, when you measure here again, you have got the heights distributed like this for this individual. For this individual again, right? And for this individual again. Now, if I ask you, are you finding a wee bit of correlation in saying that with the introduction of one allele into the genotype, what is the introduction? The introduction of this T allele. Is there an influence on height? If you take how the mean varies of this thing, there is no variation at all, right? So for such kind of a SNP, wherein when you fit a line against all the points that are distributed, if there is no slope, it means that this particular SNP has no effect on the genotype, no effect on the phenotype, no effect on the phenotype. Once again, quickly, I'm repeating this. I don't know how many of you have understood. I've just taken an arbitrary example for one of the SNPs. And for this SNP, what I'm telling you is the individual having this SNP, there are 5 individuals I've taken here. And there are 5 individuals in this thing here. And I have plotted this. And I tried to fit a line between the X and the Y axis. This is the X and the Y axis. And if you plot a line, there is a flat line because there is no variation at all. If you look at by the introduction of one alternate allele into the genotype, right? And even after this, there is no introduction and there is similar distribution of the. Now, what am I actually talking about? We'll talk about a second graph, right? And we'll talk about a second SNP. Let us say it is a G2A SNP. So what are the genotypes here? GG, GA, and AA. Right? Guys, I want you to be attentive because today we are also going to talk about matrix algebra. Okay. Until you understand these notations of 0, 1, 2, we cannot get into matrix algebra to understand what is going on in GWAS analysis. See, everything, click, and click, you get anything out of your softwares. But you should understand why is a particular thing being done in a particular software. That is the basic fundamental of a training, right? So we'll just have a look at first. We are talking, this is the first SNP which we have discussed, right? This is the SNP that we have discussed. Let us say this is SNP 1, and wherein we have told that this SNP 1 has no effect because there is no slope at all. Has no effect. There is no slope at all. Now, if you are looking at the second SNP, let us say it is a G2A SNP. What are the genotypes? And with respect to the alternate alleles, what do you have? You have a 0, you have a 1, and you have a 2. Here the alternate allele is A, the number of alleles. Similarly, we'll plot a graph. Let us say this is GG, this is GA, and this is AA. Now what shall we do? Let us say for this particular SNP, for individuals you are measuring, you have something like this. And here you have individuals like this. And here you have individuals like this. Is that clear? Now, if you plot a graph or if you plot a line, you will have a line like this running diagonally, right? And it says, like, with the introduction of one alternate allele A, there is an increase in the height by a particular slope. And what is that increase in height? This is the increase in height for a unit introduction of your alternate allele A. You understand, right? So we are trying to identify all those SNPs in GWAS which would have an effect, on the phenotype, Right? When you say effect on the phenotype, so now you can ask me a simple question, all of you. How is the effect measured, right? How is the effect measured? The effect is measured by the slope. The effect is measured by the slope. Is that clear? And that is nothing but given by beta, right, in your equations. So when you are talking about effects here, like basically you are talking about by the introduction of one single alternate allele, how is the phenotype changing? And what is the phenotype that we are considering here? The phenotype that we are considering here is the height. Is that okay? Still here? Any doubts still here? Right. So anyone with a doubt?
Yes, sir, I have a doubt.
Yeah, can you come close to this computer and ask me?
Sir, on what basis you are drawing this line? Like in first case, you draw a straight line, and here you
Okay. Good question. Maybe you thought like you understood. Yeah. See, when you have a y variable and an x variable, can you do a regression analysis? And when you do a regression analysis, you can fit a line. For all the points of xy that are here, right? How y varies with the increase in x. You understood, no? So these are nothing but regression lines. What are these? Regression lines. Now what happens if you fit a regression line? See, visibly you can make out, like, even if there is a change, a line that is fit across, right? Forget about a line first. Let us simply talk about, if you're talking about a mean of this particular entire set of observations, it will be almost similar to somewhere in around that line, okay? And if you take a mean again, it will almost be there within that line. You understood? So forget about the line first. Even if you look at the means are also similar. Now what happens here is, like, normally when you want to find out the effect, regression is done. What is done? Regression is done. So am I clear? Possibly she understood that, right? I'm assuming that you understood. Okay. Now we'll proceed. Now, when you have this slope, see, now the point is, like, you're not talking about a single SNP when you're doing a GWAS, right? When you're doing a GWAS, I was talking about a single SNP. See, this is for SNP1, this is for SNP2, I was just discussing. But when you're doing a GWAS, you're not talking about a single SNP, but we'll be having millions of SNPs. Millions of SNPs. So any analysis that is done, right, now is usually done, right, for a single SNP GWAS, right, for a single SNP GWAS. Single SNP GWAS. right? We'll talk about multi-locus GWAS later on. We are not going to discuss that in detail, but we are going to talk about single SNP GWAS. Now, what is this single SNP GWAS? See, we have fitted a line, and this is done individually for all the SNPs. Let us say SNP1, right? SNP2, SNP3, right? Now, what do you have here? I told you, you have the effect. And what was the effect I told you? Effect is nothing but the slope. It can be a minus or a plus, means what is the effect of introduction of this particular allele into the genotype, right? If at all it has got some effect, whether it is positively increasing the phenotype or negatively decreasing the phenotype. Now, let us say it can be 0.005, whatever it is, right? Effect, I'm just taking some arbitrary numbers, plus 0.10, plus 0.020, right? The next one. See, the most important thing, the next column. We are not satisfied simply by looking at the effects, guys, right? There has to be a probability attached to it. Probability attached to it. And if you, this probability will tell us, right, how significantly is this particular SNP affecting the phenotype? How significantly is this particular SNP affecting your phenotype? And normally what happens, this goes by in zeros or whatever it is, right? And you can write it as 0.00006, right? And you want it to be less than 0.05. Now, how many of you know what is probability? I want you guys to understand what is this probability. See, I assume that most of you are students, and even if you are teachers, bear with me, because this is the way generally I take a class, and I can't help it, but again, repeat the whole story over and over again, right? Okay. Now, see, the probability is what? Probability is occurrence of anything by random chance. Occurrence of anything by random chance. How many of you have really understood this? Occurrence of an event by random chance. So when you say probability is occurrence of an event by a random chance, do you want it high or do you want it to be low? You normally want anything to be true, right? For it to be true, the occurrence by random chance should be low. So this particular occurrence by random chance should be quite low. Is that okay? Right? Now, normally in statistics, what do? You take the probability less than 0.05 to be significant. Hi, Anna. Less than 0.05 to be significant. Yes or no? Okay. Now, see what is more important is the moment you take 0.05 as your cutoff value, you mean that you are taking 5 events to occur by random chance. That's what it is. 5 events to occur by random chance means there are 5 false positives. Yes or no? So now listen to me very carefully. And this analysis that we are doing here in GWAS, see, what are we doing? We have finished all this, right? We have finished we are looking at the effects. We have looked into the effects. I told you that we are doing a single SNP GWAS. And in single SNP GWAS, what did I tell you? I told you that the probability is usually measured by SNP wise, and each SNP is taken in one single go to give you a probability. And this probability is generally taken to be as low as 0.05. Even if you consider it as 0.05, right, you will have 5 false positives. Now look at this. The reason why I told you that you have 5 false positives is, right, for every SNP, if you start to have 5 false positives, because each SNP is measured individually, right? For every SNP that you start to have 5 false positives, you'll be having a huge number of false positives. So what do we do to correct this probability? So this probability is normally corrected in GWAS by a correction that is popularly known as Bonferroni correction. Bonferroni correction. So how is the correction done? Normally it is done by a Bonferroni correction. Is that okay? Now, what is Bonferroni correction? See, Bonferroni is nothing but, we'll talk about this in detail when we are talking about matrix algebra, and we'll discuss this. But have a look at this. I have divided this into 3 parts. The first initial thing is having some basics on GWAS, then matrix algebra, and what are the common problems in GWAS. So half an hour each, probably we'll finish by 3:30 or so, let us say. So Bonferroni now, for example, if you're looking at, what do you have in Bonferroni? The Bonferroni correction is nothing but the p-value is normally corrected by dividing 0.05 by the number of SNPs. By the number of SNPs. By the number of SNPs. However, popularly, Bonferroni is taken as 0.05 by 1 million SNPs. 1 million SNPs. And if you calculate this, this becomes 5 into 10 to the power of minus 8. This is nothing but, so look at this now, wherein you have considered what initially 0.05 as your cutoff, and now look what is your cutoff after Bonferroni correction. Is that clear? And this is mainly because of false positives that would increase in your GWAS analysis as you proceed SNP by SNP. And to have true positives, you will only have to consider those SNPs that have a higher p-value. Assuming that all of you have understood that, what I'll do is, we'll now slightly complicate things, guys, okay? This is the basic fundamental. We'll slowly get into it and we'll slightly complicate it. Okay, now, how many of you know matrix algebra? I'm not sure you are clear with your matrix algebra or not, but if you are clear with your matrix algebra, it's fine. Otherwise also, it's not a problem at all, right? Okay, fine. See, what did I tell you? You have basically started your class with a concept like fitting a line, right? Mx plus c. And sometimes this m is called as nothing but the slope. This is nothing but y is equal to, sometimes referred to as beta x plus c, where x is the variable. Yes or no? Right? That's what it is, right? If you are looking at a straight line, you are taking x-axis here and you are taking y-axis here. You are just, this is nothing but the equation for your straight line, right? And where beta is nothing but your slope, right? Now look at this. What is there on your x-axis? Your genotypes. Yes or no? What is there on your x-axis? X-axis is your genotypes. So your y-axis is your phenotype. So now as we proceed, right, we'll slightly convert this equation that I gave you here into an equation like this. Y is equal to beta G, where G stands for genotype, right? And C is nothing but, we'll just give it as an error, right? So the basic equation that any GWAS would fulfill is this one. Means you have to clearly understand this basic fundamental has come from the line that we have actually drawn initially by taking the genotypes on the x-axis and taking the phenotypes on the y-axis. The only thing that I've changed here is instead of x, I've put a g in the equation. Is that clear? Now what happens? You're not considering a single individual, right? When you're saying y, it is the phenotype of all the individuals. And when you are saying G, you are not talking about a single individual. It's a genotype of many individuals. And here comes in the concept of matrix. So I'll take a new page and we'll jump into the new page for that. Okay. Just give me a second. Okay. Now, what did I tell you? This is the equation. Y is equal to beta G plus E or epsilon. And this is what is the equation, right? When you look at this particular equation, Y is a set of phenotypes. So we'll run the phenotypes like this: Y1, Y2, Y3, Y4, and this will go to Yn as the number of individuals. Yes or no? Right? Please write this down if you're not writing it. And the reason why I have asked Sandeep to record this is I have not taught this anytime. This is for the first time I'm teaching. I want to have a look at like how at all this is going by, nothing else. Once I came for 15-20 minutes at NIIB and probably I took this, but yeah. Now, we'll talk about the genotypes now. And what are the genotypes now? Not a good artist, guys. You have to bear with me with this. Sometimes like my drawings may go haywire here. Okay. So we'll just draw this here, right? This is Yn. Now, we'll talk about the genotypes, guys. Now, when you're talking about the genotypes, how many SNPs do you have? You have millions of SNPs, right? So you are talking about the individual one. When you're talking about this, listen to me very carefully. This notation should be very clear in your heads. When you're talking about this Y1, this is the phenotype of the individual Y1. So anything that is coming against this should be corresponding to that particular individual. So when I simply write genotype 1, means like it is genotype 1 for SNP 1, right? Genotype of individual 1 for SNP 1. You understand? Right? Similarly, genotype of individual 1 for SNP 2. So genotype of individual 1 for SNP 3. And similarly, this will go by in the matrix form till the place where you have genotype of individual 1 till SNP M, means millions of SNPs. Is that clear? So this is how you write this. Now, are you understanding or is there any confusion? Okay. See, the basic fundamental that you should understand in matrix algebra is when you want to multiply two matrices, all of them are understanding? I can only see you.
Yes, sir. Yes.
Okay. So now what we'll do, we'll write this genotype for individual 2 here. That is genotype of individual 2 for SNP 1, genotype of individual 2 for SNP 2, genotype of individual 2 for SNP 3, and likewise it will go on till the genotype of individual 2 for the millionth SNP. And similarly, if you proceed, if you go by, come down, similarly, this will go by for the genotype of nth individual for SNP 1, genotype of nth individual for SNP 2, and likewise you can proceed, and this will be genotype of nth individual for mth million SNP, right? So this is one matrix. This is one matrix that you already have here, right? So this is one genotype matrix that I told you that you should have, right? So this is the genotype matrix which I was talking about. Is that clear? Now, what is it that you want to estimate, guys? In this line that you have constructed, what is it that you want to estimate? It is the slope. Yes or no? Because the slope will ultimately give you whether it is significant or not. If the slope is good enough, the probability will be good enough, right? If the slope is not that good enough, means the change of one allele in that genotype, how would it affect the phenotype is nothing but the slope. That's what I told you, right? Here you had 0, 1, and 2, right? And one change in this particular allele would bring about a change in the slope. That's what. So the next one that you have here is what is your effect matrix. This is nothing but B1, B2, B3, and this will run up to where? How many? This will run up to the million of SNPs. Million of SNPs. Okay, this is where matrix algebra is tricky, I know that. But anyways, so this is what it is. Now listen to me. What you should understand is, can anyone tell me what is the size of this matrix? The size of this matrix is how much? N into? When I say N is the number of rows. M is the number of columns. And what is the size of this one? M into?
1.
So if you want to effectively multiply two matrices, the number of columns of the matrix to be multiplied first should be equal to the number of rows of this. So that's how, if you say R into C should be equal to C into 1, right? So these two should be the same. And here, since you have both of them to be the same, you can multiply. And finally, what are you going to get? You're going to get a matrix of N into M. N into M is nothing but your phenotype. Is that clear? What is the size of this? This is N, is your size of the number of rows. And how many columns do you have? 1. So this is the actual combination of your matrix. Is this clear? Clear? A quick review of what we have done, right? We have just converted the slope that we have earlier looked into a straight line equation. And that straight line equation was what? Y is equal to mx plus c. And this x was nothing but the genotype, right? So we replaced x with the g, and m, which is the slope, is replaced by beta. And c, we considered it as an error, right? So we replace this. Now this, when you're looking at, you're not talking about one individual at a time. You're talking about n number of individuals for m number of SNPs genotyped on those individuals. So you'll have all these matrices written like this. You have Y1, Y2, Y3, Y4. The phenotypes running till Yn, and all the genotypes that are running till n, and all the betas that you need to estimate. Is that no? Right? Is this okay, guys? Okay. Right. Shall we proceed? No doubt still here? Right. So now, whatever we have estimated till now, any doubts? They can come to the computer and ask me if they have a doubt, okay? Right, fine. So, whatever we have estimated, in matrix notation, all of you, those who want to do GWAS analysis, listen to me very carefully. If there is, let me put this somewhere else, guys. Yeah, if you have a beta like this, and if there is no hat written on it, right? Because all of you who want to do genomic analysis should understand this. If you have a hat written on it, it is called as an estimated effect. And if you don't have a hat written on it, it is called as a true effect. Ultimately, what do we want? We want to estimate our true effects, right? But estimating the true effects with so many millions of SNPs right? Normally, we don't have a word that is called in statistics as power, right? To estimate the true effects of all these SNPs in one single go for the entire genotype data on the phenotypes of all the individuals, you cannot estimate all the true effects. Is that clear? But ultimately, what is your aim? This is your aim. This is the equation, and this is what you want to estimate. Is that clear? So this model, which you have seen here, is called as a full model. This is called as a full model. Now, since this has got a constraint that you will not have the power to estimate all the true effects in one single go, we'll have to reduce this full model to a model called as marginal model. And we'll talk about the marginal model now and what it is. Marginal model. And what is this marginal model? The marginal model is nothing but looking at one SNP position at a time. What are you doing? You are only looking at one SNP position at a time. Means you're not estimating all the betas. You're only estimating one beta at a go, right? And how are you doing that? So the equation now becomes the equation. What is the equation now? The marginal model. Guys, it's around 3 o'clock and I'm talking about matrix algebra. If you had a heavy lunch, I'm very sure most of you must be sleeping at the back, and that too in an online class. In an online class, I'm very sure that most of you are sleeping, but just have the courtesy that even it's 3 o'clock here at my place as well, and still I'm talking, right? Okay. What do you think is the attention span of a particular student? For me, it is not beyond 20 minutes. So I can't expect you that you're going to listen to me beyond 20 minutes. But however, right, just divert yourself after 20 minutes and get back into the class. Because I know that suddenly sitting in a class for 20 minutes, you'll be wondering about what's going on in IPL just now, right? Who won the match or what's going in that movie. But again, have courtesy that this fellow is still talking on the screen, right? Right. Fine. This is the marginal model. We'll talk about this. This is Y. This is genotype of the ith SNP. Sorry, genotype in the ith individual, right? The effect of this thing and effect of this one, right? So let me explain this. First, we'll write. We are estimating the effect of the ith SNP, not the ith individual, right? Don't take it as we are. See, what did we say? We are talking about estimating all the effects. We can't do it. So what are we doing? We are doing one at a time. So what are you doing now? You are first estimating one SNP at a time. Means first B1 for all this. So how does this look like? The phenotype will still remain the same because the phenotype is same, right?
Yes, sir.
The phenotype will still remain the same. It will run across for all the individuals. Now you have the genotype here. Now, when we are talking about the genotype here it is the genotype of the first individual for the first step, genotype of the second individual for the first step, genotype of the third individual for the first step. See, earlier what did we do? The same thing here. You're only taking the first column here, right? And you are running till a place where you have, for this first SNP, the genotype on all the individuals. Is that clear? Instead of taking the entire vector here, what are you doing here? You are only taking this vector here. Is that okay? And you are multiplying this with the effect. Since there is only one SNP, you are going to have only one single effect. Is that okay? And this is added with an error I, right? Let's quickly sum up this. What are we doing? This is the original genotype matrix that we'll have to consider. And this original genotype matrix will have all the phenotypes and all the genotypes. No test in the world has got the power to estimate all the effects in a single go for all the SNPs. So it has to do it SNP by SNP. So the marginal model is followed. So we're initially considering one SNP at a time. And if you are considering one SNP at a time, right? So instead of taking as one here, we'll now put it as ith SNP, ith individual, right? Jth individual, right? For the jth individual, ith SNP. So here you have first individual, ith SNP, ith SNP, ith SNP, ith SNP. For your ease of understanding, I have taken one here. Means for every SNP, it will take one genotype at a time with this model, and will give you an effect for this particular SNP. Is that okay?
Yes, sir.
For every individual, it will take one SNP at a time, and it will give you an effect for that phenotype. Okay. Having understood this, right? All said and done, what was the phenotype that we considered? Height. Right? Do you think height is only affected by the genotype? Or are there any other parameters that would affect height? Does age affect height? As the person increases in age, the height also increases, yes or no? Sex has an influence on height. Males and females, there's a huge difference,
Yes.
right? And likewise, there may be several other parameters which may affect height besides the model which I told you as the J and Bij and Eij, right? That's what I told you here, right? Whatever it is, right? Now, see, all these factors are said to be covariates, right? Now, what happens sometimes is your analysis is hugely varying in terms of age and sex. And if you're not correcting your data for these covariates, you will be having SNPs, but these SNPs will be correlating with not the genotype. These SNPs in the genotype will not be correlating with exact genotype influence, but also would be affected by traits like age and sex. So that's why, if you remember, when I told you, when I wrote phenotype, right, I left something as a blank there. Phenotype is what? A genotype
Yes.
plus environment I left, right? And something I left, right? See, these two together actually are termed as non-genetic factors. Non-genetic factors. And under this, you can have a term called as covariate. Okay, this is what we have studied, right? Now, all said and done, this is fine. Now I'll show you what exactly you people are going to do in your GWAS analysis, right? Once you feed in the data and you get it, how are you going to exactly look into it as whether it is significant or not, right? So this is how a graph looks like. So I have it. Oh, sorry, I thought whether I kept it or not. Okay, now listen to me. See, these are the millions of SNPs. Don't get confused. I'm just telling you, how are you going to interpret your GWAS analysis? Now, the point is, there are two things that we considered, all of you. I would have loved to be in person there, but I've got election duty tomorrow. Sorry about it. But anyways, yeah, probability, what did we consider? It is 0.05, right? That's what we considered,
Yes, sir.
right? And we told that this is wrong because it will be having a lot of false positives. Therefore, we'll correct what? We'll correct it for the Bonferroni cutoff. Bonferroni cutoff, right? And this Bonferroni cutoff is how much? This Bonferroni cutoff is how much? What did I tell you? The Bonferroni cutoff is 5 in 10 to the power of -8. Now, see, and I want you guys, whosoever wants to work in genomics, to by heart these two values now. I'm going to give you two values now. Listen to me very carefully. See, what are you plotting here? This is chromosome 1 here. Is that okay? All these are chromosomes. There are 30 chromosomes in cattle, actually. In cattle, you have around 30 chromosomes. You're talking about a cow. 60 pairs of chromosomes, 30 chromosomes. Now, these dots are all SNPs based on their significance. You see the probability here based on the significance. Now, what did I do? I converted the probability value that we have got into a -10 log 10p. Into a log 10p. What did I convert? I converted this values into minus log 10p. So if you convert this p value into minus log 10p, means minus log 10 of 0.05, this value I want you to remember, it is 1.3. What is it? It is 1.3, means somewhere around here. You see this value on the graph? If you want to look at this on the graph, it will be somewhere around here. Is that okay? Right? It will be somewhere around here. And look at this. If you can write at the end, right? Probably. Okay. Now, this is somewhere here. Now, if you consider this as a cutoff, guys, if you consider this as a cutoff, guys, and you say that, okay, this is a cutoff here, right? Means all those SNPs that are above this are all significant. Look at the number of SNPs that are significant here. Is that clear? So these are all false positives. If you consider p.05 and consider log 10 as 0.05 and 1.3 as your value, see how many false positives you already have. That is the reason why we take a Bonferroni. You should understand why we take Bonferroni now, right? We take Bonferroni mainly because, now look at Bonferroni. What did we do? We took Bonferroni as a value of 5 into 10 to the power of -8. Now we'll take a minus log 10p of Bonferroni. Whoever wants to work in genomics, these two values, 1.3 and this value of 7.3 should be remembered. Is this clear? This is 7.3. Is that okay? So this value that is corresponding to this particular place here is 7.3. See, we raise the bar by correcting all the false positives. And we are saying if log 10p is greater than 7.3, you are only going to consider those values that are significant. Look at the number of SNPs that are significant now. Right? It has decreased drastically, and you can count them in tens to hundreds. Is that okay? No. No. All said and done, I want you guys to have a closer look at this graph and see something that is very clear and peculiar to this graph. What is it that is very clear in this graph? You have certain peaks. You have these peaks, right? We call this as a peak. We call this as a peak. And definitely there is a peak on chromosome 6. There is a peak on chromosome 6. And when you look at the peak on chromosome 6, right, you have so many SNPs that are there. but they're close to one another. You can't even count them. They're close to one another. This phenomena of these SMPs being close to one another, I already know that you know this word. This is called as, this is mainly because of LD, linkage disequilibrium. So because of the linkage disequilibrium, now listen to me. You may ask me, sir, when this particular SNP is said to be significant, when you have this SNP to be significant, this particular SNP to be significant, right? This one, right? Does that mean that this SNP has an effect on the phenotype directly or not? You understand my question? See, I am giving you complete practical aspect of understanding GWAS. Now, what are you doing here? You analyzed it, you know the fundamental, how to feed the data, what gets into the software. I gave you the fundamental. Now, this is the output that is constructed, and this plot probably I've missed. It is called as the Manhattan plot. This plot is nothing but the Manhattan plot. So we have certain fundamentals that we have to look into, whether to see whether our GWAS analysis is good enough or not, right? Okay. All of you are there with me, or is it getting more and more monotonous? It's good? Okay. It's fine. Now, see, the point here is, want to,
Excuse me, sir.
yeah, yes, she's asking me a question.
Yes, sir. Sir, can you explain this linkage disequilibrium term?
Can you explain what?
Linkage disequilibrium.
Term. You told that this peak come because of linkage disequilibrium.
Explain. You want me to explain what LD is, right?
Yes, sir.
Oh, come on, that's an entirely different story now. Okay, good. I teach this, okay, with an example, fine. Okay. Listen to me. We have diverted from the topic anyways. It's for the good of everyone. And for me as well, I'll be revising a few things. Guys, I tell you, teaching is the best way of learning. There's no second thought of it. Okay. Now, all of you guys, if I ask you, I don't know how many of you exactly know the meaning of linkage. If on one chromosome, you have a capital A and a capital B, and another chromosome, you have a capital A and a small b, the gametes you expect would be AB and a and small b. Right? These are the gametes you expect. I think you know this, right? See, we can't go into a further fundamental. You should understand that these are the gametes. No, these two are said to be parental gametes. These two are said to be parental gametes. And these two are said to be recombinant types. Now, when you look at parental gametes, for example, if there is linkage between A and B, there is every chance that A and B will be found together always. Means the probability of getting these two gametes is higher than the probability of getting these two gametes. Yes or no?
Yes.
For example, if there is complete linkage, there will be no recombination at all. And the chance of complete linkage is beyond our expectation. But anyways, if there is complete linkage, you will be getting only parental types. Now, what is linkage disequilibrium? How is it defined? Linkage disequilibrium is basically defined by the frequency of the AB gamete, ideally, if there is no linkage, should be the product of the frequency of A and the product of frequency of B. You understand? Is that okay? When you're talking about no linkage, this is the fundamental under Mendelian genetics. Under Mendelian genetics, what are you talking about? You're talking about a frequency of AB, right? And this frequency of AB is nothing but the frequency, the allele frequency of A and the allele frequency of B. The moment that this does not hold good, right, you say that there is linkage disequilibrium. You say that there is linkage. I think now she understood. The moment, this is one of the definitions I'm telling you. What did I tell you? Ideally, under Mendelian genetics, when there is no linkage, the frequency, the gametic frequency of AB should be the product of the allele 1 and the product of the allele 2, right? At the second locus and the first locus, respectively. The moment that this does not equate, it means that there is linkage disequilibrium. How many of you understood this? All of you understood this? This is basically the fundamental of what I told you here. See, the problem is like, if the frequency of this increases, when will this increase? When there is strong linkage between these two. And when there is strong linkage, this will increase. And the normal allelic frequency that you expect, right, and you have, will not be same, or sorry, the product will not be able to be the same part of your gametic frequency. Okay. And one more is, I'm slightly deviating from the topic, but sorry, it should have been like this. See, when you write this, this is the one, right? The second definition of linkage disequilibrium is, see, these two are called as coupling phase gametes. Coupling phase, right? Why they are called as coupling phase? Because they are present on the same chromosome. And these two are called as recombinants. And these two are called as recombinants. Now, the product of the coupling phase, the frequency of the product of the coupling phase is not equal to the product of the recombinant phase. These are the two equations that you generally, you simply say frequency of this and frequency of this, right? This is normally what you have. Is that okay? These are the two definitions. When you go for any standard exam, like this is how, otherwise it's simply understood that if linkage is there, automatically two alleles will always tend to move together, right? When the two alleles tend to move together, it means like there is linkage disequilibrium, right? Forget about that. Okay, we diverted from, is that clear? Ask her whether it's clear for her.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, now, so we were talking about this. Where were we? We were talking, yeah. See, the most important thing, in GWAS study, the normal hypothesis that is tested is always as, if you take a null hypothesis, this is very important. How do you take a null hypothesis? You take a null hypothesis as genotype has no estimated effect. Has no estimated effect. Whereas alternate hypothesis is genotype has estimated effect. Now, can anyone tell me why am I I did it purposefully, right? Why am I purposefully writing it as estimated effect and not as effect directly? Genotype has no effect, I should have written it as, right? But I've written it as genotype has no estimated effect. The reason is linkage disequilibrium. Listen to me very carefully. For example, if you have a SNP here, right? This SNP may not have a direct effect on the phenotype, but may have an effect just because it is closely linked with some other SNP here, which has a major effect. You understood? So that's why you say that genotype has an estimated effect. Once again, I'm repeating this. You got this as what? You got this as, these are several things that have to be very clear. Sometimes you will think that SNP, the top hit, what is the top hit? The one it is sitting here should have a major effect. No, it is like this, like just because this particular SNP is in LD with any of the SNPs below, right? It can have any other SNP which has a major effect. And that's the reason why we say it is an estimated effect. We don't say that it has got an effect directly. It has got an estimated effect. Hope I'm clear. Right. All said and done. Now we'll look into the last 15 or 20 minutes, and then we'll start the practical. We'll look into one more important thing to say whether you have done your GWAS correctly or not. The first one, the first thing that you have to do in your GWAS is what? You have to go for your good sample size. Good sample size. Ideally should be greater than 100. However, preferably it should be greater than 300. Now, second one, right? Now here, at least as my concept goes, right? We do not filter for LD. We do not filter for LD. However, we eliminate inbred individuals fourth, we also look into the heterogeneity. See, these are all the QC parameters that you have to look into when you go for. Okay, all said and done, this fellow is telling us big stories, right? Have greater than 100, greater than 40 and all. But getting numbers, at least in animals, greater than 100 is beyond our control. Is that clear? Then what are we doing? The next question is, yes, you are saying this, that you should have greater than 100. So what are we doing? What we normally do is, we generally go for a higher MAF. This you'll understand only when you get yourself drowned into the analysis of GWAS. Is that clear? Means, see, when the sample numbers get close to, let us say, 30 or 40, and 30, 40, 30, 40, and combined sample number is around 180, right? 30 per group, right? See, when you're saying GWAS, what are you doing? You're actually comparing two groups, right? When you're saying height, right? You're comparing several things. Oh, I forgot this. Sorry, guys. 1 second. Oh, how did I forget this? There are two kinds of cases that we study. Oh, yeah. I remember this. Yeah, there are two kinds of studies in GWAS. Two kinds of studies. One is case control. What is it? Case control. What do I mean by case control? Affected by a disease, healthy. You understood? Right? Means discrete groups you have. Means you have two groups saying that, okay, this group is affected and this group is not affected. So such kind of analysis is called as case control. Second one is continuous variable analysis. Continuous variable analysis. What is this? The height that I was just talking about. Here there is no discrete. It is a continuous variable because height can vary from individual to individual for any number of centimeters or for the scale that you take. Means it can have a value of 7.3. It can have a value of 7.31. It can have a value of 7.311 as well, right? So it's a continuous variable. So there are two kinds of analysis in GWAS that you can do. One is a case control and one is this thing. So whatever you have, when you do a GWAS analysis, please ensure that the total number of individuals that you're considering per group, if it is a case control, per group should be greater than 100, right? And altogether, when you are considering, it should be ideally greater than 300. Is that okay? For the continuous variables. And your analysis would be reliable enough. Okay. Now, the last parameter, and again, we are talking about statistics. Don't tell me like this fellow is keeping on talking about statistics. I'll take a new page. Let's see. Yeah. Okay. Now, one of the major interpretations of your analysis is by looking at your Bonferroni, right? By making the Bonferroni correction. Guys, I tell you, because of lack of technology or lack of certain statistical tools, some people do not go in for Bonferroni, but I prefer that you should always select those SNPs that cross this particular obstacle of your Bonferroni value of 7.3 so that you consider. Okay, that is one major thing. And the next thing that people generally look into your analysis is your QQ plot. QQ plot. Now, what is this QQ plot and what do they do? Right? And by looking at the QQ plot, they estimate a parameter called as lambda factor. They estimate a parameter called as lambda factor. Is that okay?
Yes, sir.
Now, we'll talk about a simple example, right? To make you understand. All of you are tired listening to me or you're okay? At what time do you have tea?
4, sir.
4 o'clock. Fine. Then it's okay. Okay. Now listen to me. What do you understand by a quantile? What do you understand by a quantile? See, for example, in all those competitive tests that you have passed, you say that you have got a 99.9 percentile. What does this mean? Means below your particular score, there are around 99.9% of the people that they are there. You understood? So now what happens is, see, quantiles can be in terms of percentiles. It can be in terms of any number that you're going to take. Percentile is for like dividing all the different observations into 100 equal parts. Then you call it as percentile. So similarly, what we do here is, after the analysis, right, a graph is constructed with the expected probability values here on the y-axis, expected probability, log 10. Log 10 minus log 10 expected probability, and with the actual minus log 10 probability. Is that okay? And this is based on the fundamental that whatever probability values you have got, right, each of them has got a quantile, right? Means, for example, you have got, let us say, 100 probability values, and you have plotted them here on your y-axis, and this probability value is 0.0001. Is that okay? And now if you are looking at this particular value and you're talking about the percentile, here, what is the number that you have? You have 0, right? So this will be 100th percentile, yes or no? It will get the first rank, right? Now, if you're talking about this individual having a score of, let us say, 0.06, and you'll count the number of individuals, right? 1, 2, 3, 4, 5, and then take the fraction and say, this is the percentile, yes or no? So this, every particular value that the probability has been calculated for will be having a percentile value. For example, an individual writing a test, right, will be having a percentile value because he'll be knowing like how many individuals are below him or how many individuals are above him. And likewise, here you'll be knowing a value. So now what happens? The lowest percentile of this is, now you have a hypothetical distribution as well. Now what do? You have an expected hypothetical distribution. You have an expected hypothetical distribution. With this hypothetical distribution, you will take the lowest value of this and the lowest value of the hypothetical distribution, and you start plotting the graph. You understand? Means you have this value as, let us say, 0.05, and for the hypothetical distribution that you have, you may have a value of, let us say, 0.000 something, and you plot a value. And similarly, you start plotting a value. For all the values that you have here, you will just plot a value, and probably you will get a graph like this. And if you get a graph like this saying that, okay, all of them are exactly the same, it means that the lambda is equal to 1. Means whatever probability you have estimated is as per your hypothetical distribution for your kind of study. And when a QQ plot is plotted and you get a straight line that is exactly lying on the center for all the observations, you say that lambda is equal to 1. Once again, okay guys, what are we talking about? Once you finish your analysis, the most important thing is how to interpret your data. To interpret your data, only consider SNPs that are beyond your Bonferroni cutoff. That's the first one. And the second thing, any reviewer would ask you for your GWAS analysis is the QQ plot. And this QQ plot, it means like all the values. Now, what is it that I was talking about? Any deviation from this? Let us say you have a straight line, you should have a straight line like this, right? But your points sometimes may go beyond this, like this, or may sometimes go beyond like this. You understood, right? So in such a case, when you have graphs like this, right, your lambda may vary. Your lambda may vary. Lambda is nothing but a factor which tells about the inflation of your values. Inflation of your values means about your false positives. If the inflation factor, the thumb rule, you can take this. If the inflation factor is between 0.95 to 1.05, you can consider this to be a good lambda. Anything less than this, anything beyond this, please do not consider your lambda to be good enough. It means that you'll have to again go back and check for certain parameters, which I'm going to talk about in a few minutes. Right? Is that clear? So what did we finish? We started with the SNP data, the genotype, how it looks like, then corrected for the Bonferroni, then also looked at the QQ values, and then we also looked at what ideally your lambda should be. It should be between 0.95 to 1.05. So the good lambda, right, should be lying between 0.95 to 1.05, right? And hope most of you have understood what a quantile plot is. Quantile plot is nothing but dividing the numbers, right? Every number has got a value, quantile value. And similarly, every number in the hypothetical distribution has got a quantile value. Both the lowest numbers are plotted here, the lowest value and the lowest value here. And likewise, you keep on plotting. And once you plot, you'll get ideally should get a straight line. And no analysis will be perfect ever. So there should be certain values that should tell you whether your analysis is good enough or not. The only value that tells you is your lambda. Is that okay? Right. Okay. Guys, is Neelam there to run the analysis? Okay. She'll come over, or someone can go and call her. Like, I'll take another 15 minutes, probably 15 or 20 minutes, and then probably Neelam will come and demonstrate your analysis. She'll come down. Sandeep, I gave her a message just now. Okay. Now, what are the problems with GWAS? And why at all you don't get your, that is the last thing I told you, will. What should you correct for your GWAS analysis, and what is available in the market to correct these parameters? Is that clear? That is the last thing, probably another 10 minutes or 15 minutes, right? Now, see, GWAS is what? Simply feeding in the phenotype and your genotypes and just doing it. Now, the problems with GWAS is the first one. Population structure. And the second one is sample structure. And the third one is cryptic relationship. See, everything reflects the same. Now, for example, you are comparing Americans and Indians or Germans and Indians. Germans and Indians, by virtue of being two different groups as such, because of their population structure, right? When you are comparing them with them for height, automatically what will happen? You are not eliminating that particular event of these two individuals being different as far as the population structure is concerned. So you already know that these two populations are different.
So,
Yeah.
I'm here.
Neelam?
So,
Hello,
Sir.
Neelam?
am I audible?
Just a second. I'll finish this off and then probably you want me to initially run the analysis for and then show them. You'll go for Plink.
Yes, sir.
Okay. Let's finish this. Okay. See, when, for example, when you are doing a PC analysis, it's not, we have got no time to discuss all this PC and all, but anyway, when you're doing a PC analysis, what happens? You have a group of individuals here, right? And if you have a PC1 and a PC2 here, PC1 and a PC2 here, right? Now, you have this group of individuals as Indians. And let us say you have another group of individuals here as Germans. And the trait that you are considering is what? Height. See, already the populations are separate. Means there are certain factors, even without considering your genetic factors, they are telling you that they are different. Is that clear? So you need to correct for those factors. And how do you correct for these factors? You can correct for these factors by including these species, the principal components as covariates. The principal components as covariates. You remember, I was talking about the covariates where we talked about age, sex, and all those as covariates. So now for the first time, I'm telling you that to correct for the population structure, you can include species as covariates, right? And then probably the value, your lambda value would improve. Lambda value would improve. Now, for example, next one. So that's how the major problem with GWAS, what I told you, is a population structure, which you already know that the individuals are different. And if you have not corrected for, there'll be some false positives because of which these populations are already different, may flare up in your analysis. The next analysis is what? The sample structure. If you look at the sample structure, you exactly don't know how many of these samples have certain ancestors that may be common, right? What the sample structure is, you don't know. So both of this can be corrected by using a matrix called as a relationship matrix. A relationship matrix in your GWAS. And both of them we are going to do today. Relationship matrix in your GWAS. All right.
Yes, sir.
So these two are the things that we normally do. Now what happened? People started analyzing the data, doing a lot of things here and there, right? Using different kinds of softwares. Now, which software to use for the best kind of results? That's also a question mark, right? So people started using, like, okay, if you want, like, let us say people correct, they take the GWAS and people correct for population structure. So initially there were softwares called as genomic control, right? If you type all this, you'll get structured analysis. All these softwares would give you all the corrections for GWAS for your population structure. But none of them was correcting for the sample structure and cryptic relationship. Then people came up with an idea that, yes, it is time that we should use our LMM models. What are LMM? Linear mixed models. Linear mixed models. Where we are not talking about this in detail, but anyway, models we have already considered, where you know that the genotype is considered as a random effect, where the genotype is considered as a random effect. And all the parameters, the population structure and all, they are all considered as fixed effects. So why you call them mixed models? Because you have both random effects and fixed effects. Right. Now what happened? Getting the betas is your ultimate aim, and that too betas for your millions of SNPs. And getting this for millions of SNPs is quite a tough job by using your LMMs. So the algorithms were further modified, and nowadays they are further modified, and you have programs like EMMAX, right? Which are very efficient, which run very quickly, and which immediately analyze your data for GWAS. Right, guys, with this brief introduction, what I'll do is not a brief introduction.